Hello everybody. In this video we're gonna start with chapter 24, which is the third chapter in the textbook in the mass transfer part. And this is a chapter that is focusing more on steady state molecular diffusion. So just to be aware of how the textbook is going, we start with the chapter 23, where we go or discuss the governing equation and how we get the equation and the derivations and what are the conditions, the boundary conditions, and how do they look like, and the strategy of solution. And here in this chapter we're going to apply all these concepts in the case of steady state molecular diffusion. And we will see why we are picking this, or this is picked as the main theme of this chapter. And we will see the different possibilities or different cases where the steady state can be applied. So just to recall, this is the continuity equation, and when we say we are applying the equation in case of steady state, then this term is 0 because there is no change with time, and this is going to be the general form of the equation. And it's not going to only be the steady state case. We are going to deal with steady state unidimensional molecular diffusion. And unidimensional means that we have the change in concentration is a function of one dimension only. So if we are in Cartesian coordinates, for instance, we have x, y, and z dimensions, then it's going to be change only in the direction of z. So we don't have change in x, we don't have change in y, and this will make the equation even more simpler, because in this case it's going to be, we will not have any time dependence, no x dependence, no y dependence. So the dependence of concentration is only on the z. If it's z, it may be x, may be y, but it's only one of them. Or it may be r or z or theta in case of the cylindrical coordinates, or whatever in case of the cylindrical coordinates, spherical coordinates. But the main idea here is that you have only one independent variable, which means that the equation is going to be an ordinary differential equation, and this is going to be very, very easy to solve compared to the partial differential equation. Of course, there might be some complex equations, but they're solvable, not like the complex partial differential equations. So what we will do is we will check different cases as I just mentioned, and then see how we can apply the equations and how we apply the boundary conditions, how we solve them, and how we can get an output from these equations. So these are the cases that we are gonna cover. We have three main topics, or three main titles: the unidirectional diffusion without chemical reaction, equimolar counter diffusion without chemical reaction, and one-dimensional system with chemical reaction. So all of them are one-dimensional steady-state molecular diffusion cases. Under the unidirectional diffusion, we have steady state and pseudo-steady state. Under the one-dimensional chemical reaction or diffusion with chemical reaction, we have heterogeneous and homogeneous reactions. So the coming videos, we will keep each video to cover one of these cases. But for now, I want to highlight the difference between these two cases. So we have here unidirectional diffusion and equimolar counter diffusion, and we need to understand the difference, because this is going to make or it's important to know what is the difference, because there are many things that will be dependent on this concept. But first, before discussing the difference, I want to distinguish the difference between one-dimensional diffusion and unidirectional diffusion. They're not the same. If I say one-dimensional, it means that diffusion is taking place in only one dimension, which means that I have only one independent variable in case of steady state, of course. But unidirectional is not the same. There is a difference between the direction and dimension. Direction, it may be positive x or negative x, positive z or negative z. They are two different directions, but z is the dimension, like x, y, and z. So to distinguish between the unidirectional and equimolar diffusion or counter diffusion, let's take a look at these two photos here. So we have two components, A and B. with two different concentrations. A has high concentration on this side, and B has high concentration in this side, and vice versa. So A is diffusing from the left hand side to the right hand side, and if A is diffusing while B is stagnant, we will see a lot of cases where B is stagnant, and we will understand why B is stagnant. But let's say we have stagnant B that is not diffusing, then this is called the unidirectional diffusion. So the diffusion is taking place only in one direction. So A is diffusing while B is stagnant. But there are other cases where A will be diffusing from high concentration to low concentration, and in the same time B is diffusing from the high concentration to low concentration, which is the other way. And this is what we call the equimolar counter diffusion. And in this case we talk about equimolar, which means that the molar flux of A equals the molar flux of B. So the same number of moles going in this direction equals the same, or the number of moles going in the other direction. So this is the main difference between unidirectional and equimolar counter diffusion. So it's important to understand this, because the equations will be highly dependent on the difference between these two cases. So in the next video, inshallah, we will start with the case of steady state. In case of unidirectional diffusion, we will see the equations, we will deal with them, and we will see how we can get an output from these equations. So I'll see you then, inshallah. Goodbye.